So before we get into the primary discussion, let's review the number systems. So that would be decimal, binary, and hexadecimal. So the decimal number system is one that we're all familiar with. It has 10 symbols, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And when you reach 9, it wraps back around to 0. But what happens to the 10 that we just counted? Well, we increment the place over to the left of the ones place that we're in. So the tens place would get a 1, and then we count again. The idea of the decimal number system is that all symbols, 0 through 9, can be used in a single place, and that you can't wrap around from 9 back to 0 without incrementing the place immediately to the left of the one that you're currently in this case, the ones place. If the place immediately to the left is already at 9, then it itself can't wrap around to 0 without also incrementing the place to its left, and so on and so on. You will see that regardless of the number system, whether it's decimal, the one that we're very familiar with, or binary or hexadecimal, all of those number systems have a set of symbols that will fit into one single place within that number system. When the highest symbol for a particular place is reached, it never wraps around to the first symbol without first incrementing the symbol to its left. Each number system might be referred to by its base. So the decimal number system might be referred to as base 10. The binary number system would be referred to as base 2. The hexadecimal number system would be referred to as base 16. So one useful interpretation of this base nomenclature is that the base number, like base 10 in the case of decimal, indicates the number of symbols available for a single place. So for base 10, there are 10 symbols available for a single place. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are no other symbols available in base 10 for a single place. Each place will have one of those symbols of the 10 which are available. The other number systems we're going to discuss here are no different. The binary number system, or base 2, has a total of 2 possible symbols that can be in any given place. Those symbols are 0 or 1. You won't see any other symbols in a single binary place. Each place in binary will either be 0 or 1. And then you have base 16, which is hexadecimal. Hexadecimal has 16 symbols available for any one place. Those symbols range from 0 through 9, and then you have A, B, C, D, E, F. So that's 0 through F. Or when translating that to base 10 or decimal, you might say 0 through 15. So the hexadecimal number system is base 16 because it has 16 possible symbols that can be used in a single place at any given time. You'll never see any other symbols than one of those 16 in a single hexadecimal place. So let's compare these number systems. Here's 3 decimal digits, and we can count from 0 to 9. When we reach 9, we wrap back around to 0, but as part of wrapping back around to 0, we increment the place immediately to the left, or the tens place, by 1. And that would give us what we know as 10. And then the ones place can continue incrementing from 0 back up to 9 again. When we count from 0 to 9 again and reach 9, we wrap back around to 0. This time, again, we increment the digit to the left, or the digit in the tens place in this case. And so we would increment it from 1 to 2, and that would give us 20. And then we continue incrementing from there. When we reach a point where both of the first 2 places, and in the case of base 10, that would be the tens place and the ones place, each have the maximum symbol value, which would be 9 and 9, or what we refer to as 99. When we reach that maximum value of 99, the same sort of thing happens again. The first place, or the ones place in the case of base 10, would wrap around from 9 back to 0. That would trigger incrementing the place to its left, which in the case of base 10 is the tens place. The tens place would wrap around from 9 back to 0, and as part of doing that would increment the place to its left, which in the case of base 10 is the hundreds place. And since you're familiar with the decimal system, you can see that continues on here. And in this example, we count up to 255, or 255. Now let's show binary and decimal together. So as we increment decimal here, we're going to show the equivalent binary value. Since binary can only use the symbols 0 and 1, we see that the two numbers look very different on the surface. But the quantity they represent is the same. So a 1 in binary is a 1 in decimal. A 2 in binary is a 2 in decimal. But a 2 in binary is represented by 1, 0, whereas in decimal it's represented by the symbol 2. That's because the decimal system can hold the number 2 in a single place. The binary system can only hold 0 or 1 in a single place. If it wants to represent 2, it has to use another place, in this case the 2's place. Remember, binary is base 2, so each place can only hold two possible symbols, 0 or 1. That's why the places are named differently for binary. You have the 1's place, the 2's place, the 4's place, the 8's place, and so on. One way to look at these places is that if there is a symbol in a place, it indicates that many of the value of the place is part of the value of the entire number. So in the case of decimal, if you have 1 in the tens place, it means you have 1 10. If you have 2 in the tens place, it means you have 2 tens. Well, the binary system is no different. If you have a 1 in the binary 2's place, it means you have 1 2, meaning you have the value of 2 one time. So if you have 1 1 in binary, that would be 3, a value of 3, because you have 1 2 and 1 1. There's a 1 in the 2's place, so that's 1 2. And there's a 1 in the 1's place, which means you have 1 1. And that might sound confusing, but just remember, binary is either 0 or 1, and 0 and 1 are both very well suited to represent digital signals, either electronically or even in conversation when talking about numbers in relation to software engineering or digital electronics, and so on. That's why you'll very often hear the use of binary and or hexadecimal in software or electrical engineering discussions. We'll get to hexadecimal in a second, but keep in mind that hexadecimal is kind of a shorthand to represent binary digits in a manner where you don't have to write so many numbers down, and they become kind of second nature to programmers and engineers. They look at a hexadecimal number and they kind of know right away what binary bits are set from that hexadecimal number. So as we continue to count up here, and we get to 9, you can see that 9 looks different in binary. Of course, it's 1 8 and 1 1, which is 9. And now we'll increment further up here, and we're going to go all the way to 255, and you'll see that that's equal to all binary 1s. That's 8 1 values. And if you were to look at the name of each of those places, the 128th place and the 64th place, each of those has a 1. So if you add up all those numbers, 128, 64, 32, 16, 8, 4, 2, and 1, the total quantity or value you'll arrive at is 255. Therefore, 8 bits in binary, or 1 byte, can represent the values 0 through 255, and it does that with 8 places, each of which can have the symbol 0 or the symbol 1. And this is binary, or the base 2 number system. And if we bring the hexadecimal number system in here and we compare these as we increment up, we can see a similar thing happen, although the hexadecimal number system has different places. It has a 1's place and a 16's place. In some sense, that means the hexadecimal system is more compact than the other two systems. Decimal and binary each require more places to represent the same quantity that the hexadecimal system can represent with only 2 places. So you can see we've reached the value of 9 in all of these systems here. When we increment to the next value of 10, notice how hexadecimal can store 10 in its first place, in the 1's place. And it does that by using the symbol A to mean 10. So A is 10 in hexadecimal. So the decimal system requires 2 places to represent 10. Hexadecimal requires only 1 place to represent 10. And the binary system requires 4 places to hold the value 10. The value 10 in binary is 1 8, and 1, 2. That's 8 plus 2, which is 10. Now we're going to count up to 15 here, and notice how the hexadecimal system can represent all those numbers from 10 through 15 in the ones place of the hexadecimal system. The decimal system requires 2 places to represent 15, and the binary system requires 4 bits. Notice that 4 ones in binary, 1, 1, 1, 1, is 15. And if you add up the place values, 8 plus 4 plus 2 plus 1, you'll arrive at 15. When developers see 0f in hexadecimal, they will usually know immediately that that is equivalent to binary 1, 1, 1, 1. Other relationships between hexadecimal values to their respective binary values also become well known. It becomes second nature to the software developer or the digital electronics engineer what these relationships are between hexadecimal and binary. For example, I know off the top of my head that A is the number 10 in hexadecimal, but more importantly, I know right away that it's a bit pattern of 1, 0, 1, 0. That is 1 in the 8's place, which is a value of 8, and 1 in the 2's place, which is a value of 2. 8 plus 2 is 10. And there are other bit patterns, like off the top of my head, 64 in hexadecimal is 100 in decimal. How do I know that? Because I've been looking at these numbers over many years, and you just get used to some of the patterns and the values. When we increment one more, we are going to go to 16. 16 in hexadecimal is 1, 0. And we can see in binary it is 1, 0, 0, 0, 0. That's 1 and 4 zeros. Many developers who work with binary and hexadecimal values probably understand that 16 hexadecimal, which is 1, 0 in hex, is 1, 0, 0, 0, 0 in binary. When a software developer sees a binary value of 0, 0, 0, 1, 0, 0, 0, 0, immediately they'd probably think of the hexadecimal value 1, 0. Or at the very least, they would know that's 16. Everybody's going to have their own way of imagining these numbers or using the facilities of their memory and any imagination they have of these numbers in order to figure things out and to understand them and to recall them and to relate them to one another. This is just based on my personal experience, and I have a hunch that most developers who work with bits, bytes, C, C++, assembly, that kind of thing, are going to know right away when they see 1, 0 hex that that's 16, and they're going to know that that's binary 0, 0, 0, 1, 0, 0, 0, 0. And again, there are many other bit patterns which just become second nature because people encounter these things over time, and relating the bit patterns to the hexadecimal values or vice versa becomes second nature for many of the values. And even for values you might not encounter all the time, it's very easy to derive what the bit values will be when you understand a hexadecimal digit. So when developers see 0D in hex, they're going to understand that's 13 in decimal, and they're going to understand that the bit pattern for that is 1, 1, 0, 1. Hexadecimal is kind of this numeric system that helps you deal with binary more efficiently. So you can make your own interpretation for what you like about these number systems, but I'm just sharing my own personal experience and viewpoint. Let's advance now from 1, 0 hex to 2, 0 hex. So if 1, 0 hex is 16, 2, 0 hex is going to be 32. And you'll notice that there is a 1 bit in the 32 place of the 8-bit byte, and there's no other ones. It's just 1, 0, 0, 0, 0, 0, which is 32. And it's very easy to see that when you have 2, 0 hex, that's 2 16s. And what's 2 16s? That's 32. So it's very easy to see that 2, 0 is 32. And because hexadecimal sort of encapsulates 4 bits per hexadecimal digit, it's very easy to visualize the first hexadecimal digit being 0 is all 0 bits. The second hexadecimal digit, because it has a 2 in it, we know that the value must be 2 binary in that upper 4 bits. That's going to be 0, 0, 1, 0. So you can kind of see how it's easy to relate hexadecimal to binary and vice versa, especially when you're dealing with values of byte size. The hexadecimal digit divides the byte up into 2 digits, each one going from 0 to 15. And each of those 2 hexadecimal digits, each themselves represents 4 bits of the 8-bit byte. Therefore, if you remember the bit patterns for numbers 0 through 15, and you remember the hexadecimal values for 0 through 15, by just knowing those, you can figure out the bit pattern and hexadecimal value for 2 hexadecimal digits or 1 byte. And you can even expand that out, where you can figure out the bit pattern for 2 bytes, because 2 bytes happens to be 4 hexadecimal digits. So you can see the power in using hexadecimal as a way of looking at sort of a compressed representation of 4 bits of a byte, and how you can then apply that to understanding the hexadecimal digits that make up a full byte, which would be 2 hexadecimal digits. And then you could expand that out to 4 hexadecimal digits, or 2 bytes, or what we would call a 16-bit word, and so on and so on. Now let's increment all these numbers up to 255, which is the maximum that will fit into 2 hexadecimal digits or 1 8-bit byte. And you can see the 8-bit byte is filling up with ones. You can see the hexadecimal digit is 2 Fs, and you can see the decimal value is 255. Here is a single binary digit, and we see how it represents 0 and 1. The question is, how can we get it to represent -1 or a negative number? How about we use a minus sign, just like we write on paper? Well, that's great for human beings when they're writing on paper or on a whiteboard or something, but it doesn't really work in digital electronics because I don't know where I would put an actual physical minus sign, a human readable minus sign. So then maybe we can ask, is there a way for us to use binary to represent negative? Well, in fact, why don't we actually just add an extra bit, and we'll use that to represent the minus sign. With that extra bit in place, we can now count from +1 to 0 to -1. And then we can count back up from -1 to 0 to +1. We're able to represent -1 by using that new bit that we added. When that bit is 1, it's a negative number, and when that bit is 0, it's a positive number. That sign bit, which is that new bit that we added, is used only to represent positive or negative. The remaining bits, and there's only one remaining bit in this case, is used to represent the number. If that remaining bit is 0, the number is 0. If that remaining bit is 1, the value is 1. And whether it's +1 or -1 is dependent on the sign bit. This method of encoding the sign for an integer in the high bit is generally referred to as 2's complement. And we can extend this out to 1 byte, where the highest bit in the byte is the sign bit. When that sign bit is 0, the number is positive. When that sign bit is 1, the number is negative. By adding more bits, we can now represent higher positive values and lower negative values. Let's go through some of the values here so you can see some interesting characteristics with a 1 byte signed integer. Let's start by counting from 0 to 15 and back from 15 down to 0. And as we can see, it's pretty much the same as the way it was before without there being any sign bit. However, even though we don't see any difference when we're counting like this, it's important to remember that the other bits still do have meaning, especially in this case, the sign bit. The sign bit being 0 actually means that we're counting from 0 to 15 and from 15 back down to 0. If the sign bit were 1, we would be doing something different than counting from 0 to +15. All right, now let's take the important step of going from 0 to -1, and let's see what happens. Wow, okay, what just happened here? If you notice, all the bits turn to 1, and that is -1 in 2's complement form. Now, how did we get here? Well, first let's explain this in human terms. Now, if you look at that Wikipedia article, which you don't have to do because we're going to go through one example here, it'll explain how to convert from a positive number into its negative 2's complement form and vice versa. Let's do that with the calculator here with the number 1 right now. So what we do is we start with the number 1 in the calculator, and then we negate that value which reverses all the bits, and then we add 1, and that will give us the representation for the negative value of that positive number that we started with. If we want to reverse things and get back to the positive number, we can negate the value again and then add 1, and we'll be back at the positive number. So you can see I started at 1, negated the value, added 1, and we ended up at the -1 representation in 2's complement form, which is all the bits being 1. I then repeated that by negating all the bits and then adding 1, and I arrived back at the number 1. All right, let's try one more. Let's enter in 50. Let's negate the 50. Then let's add 1, and we'll have 2's complement form for -50. Let's negate that. Let's add 1, and we'll be back at the 2's complement form for +50. So that's the human way of looking at 2's complement and how to convert between the positive and negative values. If we just step back for a second and look at this byte value and we see all of the zeros there before we decrement and get all the ones there, what we see is we're at the lowest value for the byte. If you look at it strictly from a raw byte standpoint, like an unsigned value, when you're at all zeros, there really is no lower value from a raw byte standpoint if you're looking at it from an unsigned perspective. So the CPU, when it's decrementing from it, it has no choice but to do something, but it can't go to a lower value because 0 is the lowest value. So what it ends up doing is it ends up wrapping around to the highest possible value in the unsigned byte, which is all ones, as we saw all ones. It just so happens that all ones is -1. And that's why 2's complement works so nicely here, is it sort of makes sense. If you're decrementing the byte and you're at 0, you end up wrapping around to the highest value that the byte can hold from an unsigned perspective. But for a signed binary value, like in this case a signed byte, that bit space, if you will, below 0, which really wraps around to the highest unsigned value, which is all ones. That bit space gets interpreted a little bit differently when doing signed math and instructions. And you can kind of see as we decrement down here to 15 as an example, we can see a similar thing happens as we begin to use that upper bit space for the unsigned byte, right? So the unsigned byte has all these bits there, and as we decrement down, which is really wrapping around in a sense. But for a signed value, we don't look at it as wrapping around. We look at it as going into the negatives. But from a computer and CPU standpoint, it happens to work out very elegantly and very nicely, where we're just simply underflowing, wrapping around to the highest value the byte can hold, and that happens to represent -1, and we continue to use that bit space up there for -2, -3, as you'll see when we're counting here. Okay, now let's go lower down here until we get to the lowest possible negative number. That's the place where the lowest possible negative number meets the highest possible positive number. Let's go see what happens at that point. All right, it's going down, 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 and here it is at 128. -128 is the lowest possible negative number. And now if we decrement one more, we see that it goes to +127. Okay, let's rewind this and go back to -128. Now, if you look at -128, you can see that there's just one bit set, and that's the sign bit, and that's -128. Now, if you forget about signed arithmetic for a second, and you just imagine that you want to take the number 1 and subtract it from that value, that 1 with all the zeros, you can clearly see that there's no way to satisfy subtracting 1 from that unless you borrow from the sign bit, which is all the way over to the left. So if you subtract from -128, which is 1, the sign bit, with all zeros, there's no way for that subtraction to be satisfied unless the 64's place can borrow the 1 from the 128's place. So that would make the 128's place go to 0, and then it would make the 64's place have a 1. But then the 32's place would need to borrow 1 as well. And that triggers a whole chain of borrowing that goes on. And that chain of borrowing leads to all ones, as we'll see again as we replay this. So let's replay this and watch that, and you can see it changes to all ones. Now, if you're savvy with your hexadecimal, you'll recognize that this is 7F, or 127. And with 1 byte signed integers, that happens to be the highest integer value, positive 127. What effectively has happened here is we have underflowed from negative 128 to positive 127. But from a raw binary standpoint, looking at it as a unsigned byte, all we did was subtract 1 from the value 1 with 7 zeros. And that subtraction just naturally led from 128, which typically in an unsigned format, that would be positive 128. But a 1 byte signed integer can't use that as positive 128 because it's used as negative 128 because the sign bit is set. And the sign bit kind of dictates how these values are sort of used. And with signed integers like this, the positive side is always shortchanged 1 value. And it's the value at the highest end of its values. So in the case of a 1 byte signed integer, it goes to 127. It can't make it to 128 because that signed bit is not available to it for a positive number, because that would make it a negative number. And that's just the nature of 2's complement signed integers, binary integers like this. So when we subtract 1 from this, we're really subtracting 1 in a sense from an unsigned value that's equal to 128, and it's just simply decrementing and going down to 127. But with signed operations, like in the CPU and whatnot, it's viewed as going from negative 128 to positive 127 in what is an underflow that wraps around from that most negative value to the most positive value. This is a little excerpt for people who are into the assembly language and machine instructions of the processors that you're working with. Now, at least on the AMD/Intel processors, I've seen it on other processors as well, typically you will find this is if you see that there's unsigned operations that are supported by the CPU, which the AMD/Intel CPU architecture supports, you'll see that they have a subset of operations. These are jump operations as well as mathematical operations that are called signed operations, and they actually work based on looking at certain flags. And there's certain flags in the CPU that will get set if there's like underflows or overflows and things like that. Now, that's a little bit of a sidetrack for this discussion, but I just wanted to mention it in case you wanted to go peek at signed operations in your CPU manual, just to kind of see that if maybe you had looked at that before and it didn't make sense. You can maybe now go and look at that. And for those of you who know all this stuff, thank you for hanging in there. Okay, now let's travel back up to 0, and then let's go to the high end, which would be plus 127. Now, this may sound different, but obviously it's sort of the same thing. We're just going in the upward direction, and when we reach 127 and we increment 127 by 1, as you can see here, it actually rolls over in a sense, or overflows to negative 128, which is really just incrementing from 127 to 128 in the unsigned value. But because we're talking about signed values, there's really no way it could be positive 128 because the sign bit is set. And as mentioned earlier, that's just the nature of 2's complement positive and negative numbers. The negative side always has 1 more negative than the positive side. So in the case of 1 byte signed integer, you have negative 128, but you only have positive 127. You don't have positive 128. And the same would apply for any other signed integer. So a 24-bit integer is going to have 1 more on the negative side than it will on the positive side. Positional number systems in general, such as decimal and binary, have certain properties. Now, generally with like a number system like the decimal number system, we don't have to be aware of these properties because we use it all the time. It surrounds us from the time we're born. So it's like second nature to us to both interpret it and to use it and to perform math using it. We really just don't have to think about the properties of it on a regular basis. However, with the binary number system, since we don't use it on a regular basis, it can be helpful to revisit some some of these properties because it can help us understand certain subject matter within, let's say, software engineering that relates to the binary number system and positional number systems and their properties. So some of this stuff I'm going to recap might be second nature for some of you guys out there, and for other folks it might just be a good refresher. Whatever the case is, I just wanted to touch on these points before we go into the next section. Two such properties I want to highlight at this time are that each digit place in a number system such as binary or decimal has what we'll refer to as an index. The index is to the left of the point, the radix point, or we would call it the decimal point in the decimal number system, or the binary point in the binary number system. But each digit to the left of that radix point, whether it be explicitly there or invisible, you might not always see a decimal point, for example, but it's implicitly there. And each digit to the left of that will have a number starting with 0, and then the next one will have a 1 and a 2 and a 3. We've seen this when we've numbered some of the digit places in the past sections. Each binary bit has an index position starting at index 0. Then you have index 1, index 2. When you take the base of the number system, whether it be base 10, so the number 10, or base 2, which would be the number 2, and raise that base to the power of the index of the digit place, you arrive at the value that each digit in that place contributes to the number's overall value. So for example, in the decimal number system, the ones place, which we're very familiar with, that would be index position 0. If we take the base, which is 10, and we raise it to the power of 0, we arrive at the number 1 because any number raised to the power of 0 is 1. And each digit in that place contributes a value of 1. So if we multiply 10 to the 0 times the digit which is in that place, we arrive at what that place is contributing to the overall number. Well, because 10 to the 0 is 1, multiplying the digit in that place to 1 just is the digit itself, and that matches up with what we know about the ones place. Whatever the digit is that's there is the value that it's contributing to the overall number. If we move to the tens place, that would be index position 1. The ones place is index position 0. The tens place is index position 1. Well, if we take the base, which is 10, and raise it to the power of 1, well, 10 to the 1 is 10. Any number raised to the power of 1 is the number itself. So in this case, the number 10 raised to the power of 1 is 10. That means each digit in that tens place, in that place which has an index position of 1, each one of those contributes a value of 10. Therefore, you can say that the value of the tens place is 10 to the 1 times the digit which is in that place. If you have the digit 5 in the tens place, 5 times 10 to the 1 is 50. Therefore, that digit's place is currently at that time contributing a value of 50 to the overall number. And if we move to the hundreds place, the hundreds place is index position not 0, not 1, but 2. It's the third digit to the left of the decimal point, or what we might call the radix point if we're going to be more technical. And so since the index position is 2, we would take the base, which is 10, and raise it to the power of 2, and we arrive at 10 to the 2, which is 100. That means every digit in that place that has an index position of 2, that's the third place over, contributes a value of 10 to the 2, or 100. Therefore, if we have a 3 in the place that has an index of 2, which we call the 100s place, but in this case, let's just say it's the digits place that has an index of 2. Well, 10 to the 2 is 100, and if we multiply that by 3, we come out with 300. So at that particular point in time, that digit would be contributing a value of 300 to the overall number. Now, we take those mechanics, if you will, for granted when we're using the decimal number system, because we kind of know, well, that place is the hundreds place. So if you have a 3 there, it's 300. We just kind of know it. We don't say in our head, well, 10 to the power of 2 times whatever the digit is there. But when discussing positional number systems in mathematics, it would not be uncommon to raise this point where you can actually, and no pun intended there, and raise this point that, if you take the base of the number system and raise it to the power indicated by the index position of the place itself, you arrive at the value that each digit in that place contributes to the overall number. The binary system is no different. Each digit's place has an index, so we know that the first binary digit has an index of 0. The second binary digit has an index of 1, and so on. Now, binary is base 2, so it only has two possible digits per place. The possible digits are 0 and 1. Now, the value of 0 really contributes 0. So the value of 1 is the only non-zero digit that contributes a value to the overall number. Now, the actual value that a 1 in any given place contributes really depends on which place it's in. If the value of 1 is in that first place, it'll contribute a value of 1. If a value of 1 is in the second place, it'll contribute a value of 2. But how can we break this down and relate it to what I just discussed about raising the power of the base? What we can say is the base is 2, and if we raise 2 to the power of the index of the position of the digit, we'll arrive at the value the digit of the place contributes to the overall number. Since binary only has one non-zero digit, there's really only one digit that can contribute a value to the overall number, and that's 1. So for the first binary digit, which is in index position 0, you would raise the base 2 to the power of 0, and we know that any number raised to the power of 0 is 1. So any digit in that first place contributes a value of 1 to the overall number. And since there can only be one non-zero digit in any binary position, and that would be the value of 1, we would say if you have a 1 in that first place, you would say 1 times 2 to the 0, which would be 1, which would end up being 1 times 1, which ends up just being 1. We would say that the place with index position 0 contributes a value of 1 to the overall number. Moving to the next place over, which we sometimes call the 2's place if you're familiar with the binary system. But instead of calling it the 2's place, let's say that second place over has an index position of 1. And if we take the base, which is 2, and raise it to the power of that index position, which would be 1 in this case, well, any number raised to the power of 1 is going to be the number itself, in this case 2, which is the base. So 2 to the power of 1 is 2. So any digit in that second place, we would multiply it by 2 to the power of 1 to arrive at the contribution that digit makes to the entire number. Well, the only non-zero number that can exist in any digit in the binary number system is, as I mentioned before, 1. So if you have a 1 there, you would say 1 times 2 to the 1, which is 2. And so 1 times 2 is 2. And we would say that that 1 there contributes a value of 2 to the overall number. Makes sense, right? Now, if you had a 0 there, you would just be saying 0 times 2 to the 1, and anything multiplied by 0 is going to be 0. So there's no contribution to the overall value when you have a 0 in any given place. So if you have a 0 in any given place in any number system, really, it's really going to be an indication that that place is not contributing to the overall number at that point in time. Now, if we go to the next place over, that would be the third index over, which would be not index 0, not index 1, but index 2. That's the third index over. So 2 to the power of 2 is 2. So we would say whatever digit in that place multiplied by 2 to the power of 2, 2 is the base, raise it to the power of the index is 2, so 2 to the power of 2 times the digit, let's say there's a digit of 1 in there, well, that would contribute a value of 4 to the overall number. And this continues in the binary number system for any number of digits we have. So we're working largely with a byte right now for explanatory and illustrative purposes, so you can see that each binary digit's place in a byte has this principle that you can apply to it in order to figure out what the overall value is. If you were to take each digit that's non-zero in a binary byte, and you were to multiply it by 2 to the index of that position, and you were to add all those together, you'd come up with what the value of that overall byte is. There are 3 remaining points I want to mention regarding positional number systems, especially as they relate to the binary number system. Notice how when this binary bit is shifted to the left, it is multiplied by the base of 2. So basically every time we shift the digit to the left, we're multiplying it by the base. And in this case, it's the binary number system. So each shift to the left ends up multiplying the overall number by the base, which is 2, or multiplying the number by 2. Likewise, when we shift to the right, each time we shift to the right, we end up dividing the overall number by the base of 2. Each shift to the right divides by the base, and in this case, the base is 2, so it ends up dividing by 2 for each shift to the right. Each shift to the left multiplies by 2, each shift to the right divides by 2. And in this small example of magnitude, notice how when we only have one bit, we can only represent 2 numbers. If we add a bit, we can now represent 4 different numbers. And when we add a third bit, we can represent up to 8 numbers. Notice how when we add a bit, we double the the overall numbers that can be represented with the bits that we have available. So when we went from 1 bit to 2, we went from being able to represent only 2 different numbers to 4 different numbers. And when we added a third bit, we went from being able to represent only 4 different numbers to being able to represent 8 different numbers.